Okay, in this video we're going to finish the lesson from Monday, September 24. The 12:30, well, neither the 12:30 nor the 2:30 section finished all the way through this. I'm going to start where we left off in the 2:30 section because that was a little bit less than where we left off with the 12:30 section. So we stopped about here. We had just found epsilon y and gamma xy here such that we could find our principal strains. And then after we did that, we found our theta p. We figured out which principal strain went with that theta p by using the strain transformation equation. And the next thing we have to do is figure out what the maximum shearing strain is. The next page here, we have to acknowledge a very important point, and that is that we do not have plane strain, which means that epsilon z is not zero. Epsilon z is not zero, so we have to find epsilon z with the equation that's listed here. And this is basically showing us epsilon z as a function of epsilon x and y and Poisson's ratio right there, that little new variable. So let's put in our values here. We have 0.33 for nu. By the way, I'm sorry about the little pen noises on the microphone. I tried to use a wireless mic, but it couldn't get it to work, so you got little pen noises. Epsilon x is 875. Epsilon y is negative 525. And that's going to give us, for epsilon z, a value of negative 172 microstrain. Now, to get gamma max, we need to identify which is the maximum principal strain and the minimum principal strain. And in this case, that's epsilon p1 and epsilon p2, which are 1050 and negative 700. So that's going to give us 1750 microstrain for our gamma max. Now what we want to do is sketch what these strains look like, and we can sketch that like we've done before. We know that theta p is negative 18.4, so we'll draw a little negative angle down here. Theta p is negative 18.4 degrees, and we'll draw a dashed box as the starting shape of our strain element, and then we have a positive strain we have a positive strain in one direction and a negative strain in the other direction. Basically a tensile strain. Whoops, I don't know why that happened. We've got a tensile strain in this direction and a compressive strain in this direction. So epsilon p1 is 1050 microstrain. Epsilon p2 is minus 700 microstrain. We can also then sketch the shearing strain a little bit different way than we've done before. Instead of drawing a separate box at 45 degrees, I'm going to put a diamond shape in here, which is basically turning the box at 45 degrees. So that's our original undeformed shape, and then if we deform it like we had on that previous little sketch, so we can imagine what the deformed shape of the diamond is inside that box. So this angle here is going to be our pi over 2 minus gamma max. In this case, that's pi over 2 minus 1750 microstrain. And that's our sketch for our example problem. Now, the next topic that we're going to do is a little bit that involves connecting stress and strain. So let's go to the next page here. stress strain diagrams are basically what we derive from tensile test machines, like you see here on the right. And the first question there just says, why use stress strain diagrams instead of force versus displacement? Force is basically what these tensile test machines are measuring. They're measuring force with a load cell that's connected to this grip right here, and as the grips move apart, they're also measuring how far they're moving apart. So they're measuring displacement. So force and displacement would be pretty much really straightforward to plot, but instead we plot stress versus strain. And the reason for that is because that's going to make our plot be independent of the size and the shape of the specimen. It only depends on the material. So if we didn't do that, then we might have to. We might have to write. We might have to do a test on all kinds of different shapes and sizes of parts. But if we instead have a stress versus strain, we're basically dividing out anything that would be related to the size and shape. So we can use it for any size and shape because the stress strain diagram only depends on the material. Typically, when we do these plots, we're going to make stress, or we're going to calculate stress as F over A0, which is basically F over. I'm not sure why I'm getting these extra lines here. That doesn't happen when I'm in class. This is basically the force over the initial area, and as we stretch a given specimen, it's gonna contract a little bit in the lateral direction because of Poisson's ratio, and the area is not going to stay constant. But when we calculate these things, it's easier just to assume that it stays constant. So typically, we use this definition of stress, which is often called engineering stress. If we talked about the actual cross section, then that's usually called true stress. That's not nearly as common to do in stress strain diagrams. So if we take a look at an actual stress strain diagram, we'll get something that looks like this. One thing to keep in mind is that this diagram on the right, where we have this piece right here that I'm highlighting, that's just a zoomed up view of something that's right along the edge of the plot right here. And you can see that there's two different scales in the bottom here for each of those different plots. But it's the same plot, just one is zoomed up. And the slope of this straight part here is our elastic modulus, which we specify as E. And one thing that you'll notice up at the top here is the ultimate strength. That's the spot at which the material can't support any more stress than that. That's the ultimate stress that it can take. Now, if you look to the right, there's a test that's been done here, or I should say a plot that's been done here, where we've gone past the proportional limit, past the elastic limit, and we've gone to a point up here where if I take the load off now, I've got some permanent deformation, or plastic deformation. So if we push something far enough, it's going to deform permanently instead of just elastically. In this class, we're basically always going to be doing elastic deformation. In a class like manufacturing, that we'll do for mechanicals, we'll take that in their senior year. In manufacturing, we're always talking about plastic deformation because that's typically what you're doing with a with machining operations or punching or stamping operations is permanent plastic deformation. If we move on to the next slide here, for a certain amount of load, stress and strain are proportional. And that basically just means that the stress is just going to be the elastic modulus times the strain, all right? And it's just linear, all right, until you get to the point where you're past the proportional limit or past the elastic limit, and then it's no longer just a linear relationship like this. We can say a similar thing for shear strain. So for shear strain, I can say tau, shear strain, is just equal to G times gamma. And this G is known as the shear modulus. So analogous things for normal stress and shear stress. Other terms you should familiarize yourself with are listed below here. Those can be found in the reading. And that's the end of this lesson. So let me know if you have any questions.